All right, thank you very much for watching this video. And this video is about solving a question. And you can see the question there. I'm going to take in time to explain the solution to this question. We are told that a car of mass 1,500 kg is constructed so that its frame is supported by four springs. Okay, take note of that. Four springs. Each spring has a force constant of 15,000 Newton per meter. And there are two people in the car. They have a combined mass, a total mass of 170 kilogram. We are to find the frequency of vibration of this car after it is driven over a pothole on the road. So we are going to model this car using the four tires. Let's assume that each tire is connected to a spring. And since the tires are four in number, which means the way the springs are arranged, or we can say the springs are arranged such a way that they are in parallel to each other. Okay, let's say these are the four springs. We must understand the arrangement. Okay, so these are the four springs. So the way and manner they arrange makes them look hard. And we are told that the spring constant of each, they are all identical spring, is 15,000 Newton. That is spring constant of each. So that the total spring constant K capital, let me use the uppercase letter here, will be given by 4 times the spring constant of each. That's the advantage of arranging springs like this. At least you can have an overall spring that have a very large spring constant. Though we know that the total extension is sacrificed in order for us to have a greater spring constant. I'm going to multiply 15,000 by 4, and that gives me 60,000 Newton per meter. All right. So Newton per meter is a unit of our spring constant. All right. So we don't need the extension here. Okay, quickly, let's see. We need to find the frequency. But before then, we need to know that the total frequency is given by 1 over 2 pi square root of k over m. I've derived it before. If you don't come across this, you can make reference to my video. Expression for the frequency of a vibrating system, mass spring system. Okay. All right. Quickly, we are taking pi as 22 over 7, and then the mass of the entire, both the car and the two persons inside the car. Total mass gives you 1,500 plus 170. Okay, so that gives you 1,670 kilogram. We want to use as total mass. So my frequency, it gives me 1 over 2 pi, 2 times 22 over 7. Okay, square root of 60,000. That is my spring constant over total mass 1670. Okay, very quickly, I'm going to simplify that 60,000 divided by 1670. That gives me 35.9. Let's take it as roughly 36. So I have this equals 7. This 7 goes up over 44 square root of 16. Sorry, 36. Alright, so that gives me 7 over 44 times 6 over 1. Alright, that's 42 over 44. So I'll quickly divide 42 by 44, which gives us 0.958. So this car begins to vibrate with a frequency of 0.958. Okay, so that's how to quickly solve this question. And one thing you need to notice that in most car systems, they do not allow the oscillation to continue for a while. So the spring systems, they are dammed. You can insert them in, a column of oil so that the oscillation can quickly go down to 0. And that shows that there are different types of damping. And when you say body, the motion of a body is damped, damping means the oscillations are of decreasing amplitude, you know, meaning that the body is losing energy, because if the amplitude is decreasing, it means the body loses energy. That's to say the oscillations are damped. That's why we have, critical damping, over damping, and underdamped. The undamped oscillation means the body oscillates without loss of energy. That's an ideal case because it's not always possible. Okay, we'll end this video here. Next video, we'll take another question.